Okay, so Marharyta, the virtual floor is yours. Please go ahead.
Thank you. So I'm sharing my screen now. Okay, you should be able to see it. So finally, as was already announced, the third part of this series of the lecture. And I would say this is probably my favorite one because it is the mostly connected to machine learning. Even in the name, we have causal learning or alternative structured learning. So now we will be talking about when and under which conditions it might be possible to identify the structure of the graph. Like, for example, which variable is the cause and which variable is the effect from the observational data. Of course, it is not very easy, and we already saw all this theory of causality essentially is based on the layers of assumptions, so we'll also need some assumptions here as well. So let us start. Last time we spent some time to understand the theory behind the Bayesian networks and DAGs, and it is not for nothing. We already used it to be able to identify when we can measure the strength of the causal effect, and now we'll use the same theory to discuss when we can identify the structure of the graph. So let us just briefly recall what were the main building blocks, because now we'll be using it to do the causal learning. So we had the three main building blocks: chain, fork, and inverted fork. These are all building blocks that consist of three nodes, and we know that the two nodes that are directly connected with an edge always have association in the data set. So when we take our data set and we measure association or correlation between these two variables, we will have some non-zero value unless the strength of the causal effect is zero, something like that. The question was, will we observe any association between non-adjacent nodes, like for example here x1 and x3? And we saw that depending on the structure, sometimes we do, sometimes we don't. In particular, when we have chain and fork, normally association does flow between the two non-adjacent nodes, and it flows in both directions because association is a unidirectional measure. However, if we block the middle node, and this is similar to conditioning and standard conditioning for discrete data set, or including the variable inside the model for continuous data set, then this path is blocked, as we discussed last time, and the association will not be flowing anymore. So when we condition on the middle node, we will not observe association between these two non-adjacent variables. However, inverted fork is fundamentally different. In fact, it is inverse. So when we don't have the conditioning on the middle node, the association path is blocked. However, if we add the conditioning on the middle node, then the association starts flowing in between these two non-adjacent nodes. Now I will show you how these ideas can be used to try to recover the structure of the graph by using the PC algorithm. We'll use this example for an illustration. So we'll assume that our data is coming from such data generating process. That is, there are four variables, x and y are the causes of z, and z is the cause of w. And we will follow this algorithm and show that for this particular case, it is possible to fully identify the same structure. So let us go through it. The first step of the algorithm starts with the following. We start with the complete undirected graphs. And let us go through the steps of this algorithm. So this is shown here. We just have our four variables, and we build a complete undirected graphs. It means that all pairs of nodes are connected, and there are no edges. There are no directed edges. That is, we don't know which variable is the cause and which variable is the effect in every pair. Next, what we will do, we will start testing unconditional independence. So it means that we will just test the independence between these two variables without any conditioning. And if we observe that the two variables are unconditionally independent, then we can eliminate the edge between these two variables. So as we said, the two connected nodes will be always related to each other. And if we test and they are independent, it means that there is, unconditionally, it means that there is no direct link between them. So let us have a look on this example. We will observe here that there is no dependence between the nodes x and y. And why? Let us see what are the kind of paths that are in between these two nodes. There is only one path like this, and it is a V structure, and we don't have the conditioning on the middle node, on the collider Z. It means that this path is blocked. So there is absolutely no associational flow between x and y. That is why we can remove this edge, and we will move to the next step. Next, what we'll be doing essentially, we'll be searching for forks and chains for this and this structure. And we know how to identify it is essentially that when we condition on the middle node, the two variables should become independent. This is what is happening in this third stage. For each pair of variables, A and B, having an edge between them, and for each variable C with an edge connected to either of them, eliminate the edge between A and B if A and B are independent, given C, that is conditionally independent. And this will let us move from the picture labeled C to the picture labeled D. So let us see what happened here. We remove this edge between X and W. It is not present here. And we also remove the edge between Y and W. Let us see how it happened from the data. So we are checking if, for the first case, let's say Y and W are independent, conditioning on some other variable. Let us see when it can happen. If we consider Y and W, this is the only path between these two variables. And we see this is an example of the chain. So when we condition on Z, the two will become independent. That means that this condition is satisfied. Now, a similar example, the relationship between X and W. Again, this is the same structure. This is the chain. And we know that by conditioning on Z, the association will not be flowing between X and W anymore, so we can remove this edge. This is the illustration of the third step. Now, in fact, on the step 4, we'll be searching for the same type of structures, but of larger size. That will be, again, analyzing two variables, but we will be checking if they become independent, given a set of variables. We'll start with 2, with 3, and so on, until we until we analyze all the combinations. So essentially, the idea will be checking the same types of structures, but of the longer size. Here, in this case, we cannot condition on more variables to see something interesting in this example. So we'll move to the next step. Here I labeled it 5. And on this step, we'll be searching for these structures. So we'll consider a triple of variables, x, b, and c, such that a and b are adjacent. It means there is a node, an edge between them. B and c are also adjacent, and A and C are not adjacent. So we have A, B, and C. Let's say A, B, and C. And we said that A and B are adjacent. B and C are also adjacent. And A and C are not adjacent. That means that there is no connection in between these two. Now, what we will check? We can do the edge orientation like follows. We can orient the edge like this. That is to get the inverted fork structure or the collider structure, this one. If variable B was not in the set conditioning on which A and C became independent. And just think about it. So essentially it corresponds to this structure. It means that we already identified that the these two nodes are independent without conditioning on the middle node. So it means it can be only a fork. So in this case, after doing these all tests, we will be able to identify this inverted fork structure, because when we removed the edge between x and y, we were not conditioning on z. Remember, this was done in the first step because they are unconditionally independent. It means that this is a collider, and we can orient these edges like this. So this will continue. We'll analyze all possible structures that might be forks in our model. And then the final step will be orientation propagation. And the idea of this step is essentially to orient the edges in such a way that we don't create additional collider structures. Why? Because all the colliders were already identified on the previous step. So what we will be doing, we already have our partially identified graph, and now we will propagate the orientation. So we have now only this edge that is still not oriented between z and w, and there are two possible options how we can orient it, either like this, z is the cause, w is the effect, or like this, w is the cause and z is the effect. However, if we use the second option, then we can see that we introduce two more collider structures. One is YZW, and another one will be XZW. However, all of them should have been already identified on this step. So this direction is not possible, and there is only one direction that is left for us, and this is it. Now, I would like to demonstrate to you essentially the same reasoning, but with the code. So we will do all the same steps, but we'll see how it works with the code. Yes, so you should be able to see my screen now. What we are going to do here, again, I will use the same library to build the data generating process the way I want it to be, because I want to test if I'm able to identify whatever is present there. And this is the same structure that was just shown on the slide. So we have y, x, they are the causes of z, and then we have z being the cause of w. And we will try to go through the steps of this PC algorithm. Additionally, we are going to do independence testing. So here we'll have unconditional independence and conditional independence, and my variables will be discrete. Here I made it simple. To do the independence test, I just test if they satisfy the probability condition of independence. I will just probably show it on the slides. It's easier again. So we know that two variables are independent if we can factorize the probability distribution. A and B, if they are independent, we can write that this is equal to probability of A multiplied by probability of B. So this is essentially what I will be using as the criteria to identify the independence between these two variables. And when I will be talking about conditional independence, given some variable C, what it means, I will just be splitting the data set according to the values of C and checking the unconditional independence inside. Of course, I will be doing some numerical computation, so there will be some error. That's why I will be comparing if these two quantities are equal up to some small threshold. I'll come back to sharing the code now. Okay, so these are my functions for testing the independence, both unconditional and conditional. And let us go now through the steps. So the first step, we build the fully connected graph. So this is the structure. Next, we start testing unconditional independence. So here, why am I doing this demonstration is to show you that this is done from the data set that we generated sampled. So here I sample the data set with a particular size, and I will be using now this data set to test all the independencies into all the conclusions. We are testing unconditional independence. So this is the function that I am using is independent, that I say this, take this variable and take this variable and tell me if they are independent or not. And these are the results. As before, we see that x and y are independent. So it means that we can remove the edge between x and y. This is what is done here. Next step, we start checking conditional independence by conditioning on one variable. These are all possible combinations of the test that I will perform. So, for example, in this case, I will test if x is independent on z given w, and so on. So I'm calling my function test conditional independence of one variable and the second variable given some condition. Here are the results, and in two cases we got true. We have y and w are independent given z, and we have x and w are independent given z. It means that we can remove the edges between y and w and x and w. This is what is done here. Then we will continue, but with conditioning on more and more variables. It doesn't make sense in this small example, so we'll directly move to the next step, that is searching for these structures. So now, how we can have these structures in this graph, in this partially directed, partially identified graph. There are three possible cases where we can observe these structures here. So we have WZY, so WZY, this is one possible V structure. Then we have WZX, another possible V structure, and the last one, XZY, XZY. Now we just need to test all of them, and our test will be, for example, for the case XZW. When we remove the edge between XZY, the question is, when we remove the edge between x and y, were we conditioning on z? And if no, then it means that this is the V structure. Let us come back. We remove this edge between x and y on the very first step. Test unconditional independence, remove edge between x and y, so we're not conditioning on anything. It means that we can orient this part as a V structure, as ZY. However, for all the others ones, WZY and WZX, we were in fact conditioning on the middle node. This was done here. X and Y conditioning on Z. So we cannot do anything. This is what we will get at the end of this step. And then finally, orientation propagation. As we said, for this HZW, there is only one way to orient this graph without adding additional V structures. So it will be from Z to W. This is it with the PC algorithm. Any questions, or should I continue? Okay.
I think you may continue.
Great. So an important note. So we saw that it worked, and in this case, it worked like it allowed us to identify the structure completely. However, there are some assumptions when we can use this algorithm. I will not be going too deep into all of them because it requires some understanding of the theory. I will just talk about the very simple one, no unobserved confounder. So here, in order to be able to use this algorithm and to make the conclusions that we made, we need to make an assumption that there are no unobserved confounder, because as we know, if there is an observed confounder, it can introduce additional dependencies in the data set, which will not be able to test because we are not able to perform all these conditional independence tests. Another one is that all the independencies present in the data should translate into graph, but it can be violated, for example, for the following case, very easy case. If we have such a structure, We have, for example, our X, our Y, our cause and our outcome, and then two intermediate variables, A and B. We see that there are two causal paths like this. However, it might happen that they are canceling each out. It's canceling, sorry, each other. So let us assume the total flow of association, or causal association flowing through this path via A is, let's say, 0.1, and the total strength of causal association flowing through the second path is minus 0.1. So they're canceling each other. It means that when we will be testing the independence in the data set, we'll observe that X and Y are independent. However, there are paths in between them. They are just canceling out each other. This is another simple thing that can happen. However, it is not that, it is just one of the possible situations, and maybe others are more probable. So before using this algorithm, you should also know what are the assumptions behind. This is also not the only algorithm. So this is in fact developed in for the task of orientation of Bayesian networks. And there are other types of algorithms. So some of them might be more useful in some situations, in other situations. And all this group of algorithms, they are based on testing conditional independence, and what they guarantee to us is to identify the skeleton of the graph. And the skeleton of the graph is defined as follows. The skeleton of the graph is defined as all the edges of the original graph without orientation. So assume that there is no orientation, plus orientation of the V structures. So in this case, we can additionally orient this structure, these two edges, and these two, because otherwise we will create a new V structure that is not present in the original graph. So this group of algorithms, independence-based algorithms, they guarantee that they will identify to us, given all the assumptions are satisfied, this skeleton of the graph that looks like this. We can see that for this particular example, we were able to orient only 3 edges, and many of them, I will take another color, remain unoriented. So we don't know which variable is the cause and which variable is the effect. And there is a theory that shows that we cannot do anything else, anything more, if we don't put additional assumptions. But let us now discuss what kind of additional assumptions we can put to solve this problem. So first, I would like to demonstrate how the same algorithm, PC algorithm, will work for this very simple case. When we have bivariate case, we have only 2 variables, X and Y, and X is the cause of Y. We'll see that all that we can identify is the skeleton that looks like this. Let us go through the steps. First, we construct a complete undirected graph. So it will look like this. This is just complete undirected graph. Then we start testing unconditional independence. There are only 2 variables. So we can test unconditional independence between them, but given that there is a direct node, we know there will be dependent. So we cannot do anything on this step. Next, we'll be testing conditional independence with one conditioning node. However, to be able to do it, we need to have at least 3 nodes in our graph. Here we can have only 2. We have only 2. So this step we'll skip. We'll also skip this step because here we're essentially conditioning on sets that contain even more variables too. And finally, this step we'll also skip because, again, to identify this structure, we need at least 3 variables. The step number 6 will be also skipped because this is orientation propagation, and again, it involves minimum 3 nodes. So this is what the PC algorithm will give us as a result for this small case. It seems to be the easiest because, or something, the type of the structure is very easy because it contains like minimum number of information. However, for the task of causal discovery, structure learning, this is one of the most difficult cases because here we cannot use any additional steps of this algorithm. However, not everything is lost. Let us now, I will present one simple idea and then another method that can help us in this situation. So the very first simple idea is called simplicity assumption, and I will illustrate it graphically. So let us assume that we have a data set with two variables x and y, and here we have a scatter plot of distribution of the values that we get, presented like this. If we assume simplicity assumption, then in fact we can identify the direction in this structure. Indeed, let us assume that y is the cause and x is the effect. So we have x is some function of y plus some noise. Then what we observe, for some value of y, there are multiple possible values of x that are available. Of course, this can happen, but this model will be some distribution with two clusters of two clusters of the density. So this model is more complex than an alternative model, that is y is the function of x plus some noise, because in this case, for every value of x, we have only one corresponding value of y. Now, question, does this simplicity assumption make sense to be used in practice? And what I want to highlight now is that all our traditional machine learning techniques are based also on this simplicity assumption. Let us talk about regression. So if we want to build a regression now for this simple model, we know that we can have a regression like this, maybe then the linear case, or we can try to build a very accurate model that will go through all the possible data points in our data set. And we know that we usually prefer the simplest model that is good enough to explain what is happening in the data set. So in fact, already here, the same assumption was used. Among possible combinations, among possible models, we choose the simplest one. This is also done when we were analyzing these two cases. Finally, this will be the last portion of material that I will be presenting in today's lecture. Let us consider how we can orient this two-variable case. Then we have the model containing only two variables, let's say x and y. We know that they are connected, but we don't know which variable is the cause and which variable is the effect. And here we'll be using so-called RESIT method and additive noise models. So here what we'll be assuming, we'll be putting an additional assumption on the structure of the dependency between these two variables. So let us assume that we have a linear function. The data is generated from the function that is x is the cause, y is the outcome, and there is a linear dependence. And what is the most important? That we have additive noise. That is, noise is added to the calculation process when we identify y, and noise is independent of our causal variable. And in fact, this assumption makes sense. So many times in practical applications, noise will be independent. And for this case, we will see that it is possible to identify the direction of the causal relationship. Here, I will consider three possible cases of the types of the distribution. We'll consider Gaussian distribution, uniform distribution, and super Gaussian distribution. So we will assume that both x and the epsilon or the noise are distributed according to the same type of the distribution, and we will discuss in which cases we can identify the causal direction. We'll be using RESIT method. Now I will explain what this method stands for, how it works. So we start with our data set. We have the distribution, the scatter plot of the points x and y. So we just have the scatter plots. And then now we'll be doing regression. The name of the method, by the way, RESIT, stands for regression with subsequent independent test. First, we'll assume X to be the cause and Y to be the effect. So we'll build a regression line. We'll regress X on the value, Y on the values of X. We'll get this line. Next, what we can do, we can build our approximation of the noise by calculating the residuals. So essentially, I will take the real point and the predicted value. I will calculate this difference between them, and this will be the residuals. And here, I will construct a plot of my assumed to be cause and approximation of noise, that is residuals. And what we will be doing, we'll be now checking if this assumption of independence between the cause and the residuals is satisfied. So it should be satisfied for the case when we are analyzing the cause, and it should not be satisfied when we are assuming the wrong causal direction. So for this case, we will be trying to do it graphically, visually. And independence essentially means that there is no particular structure between X and our residual. So there is no dependency between these two variables. And later in the code demonstration, I will show you also an example when we can calculate this independence with some function. In this case, there is no particular structure, so it seems like X and epsilon are satisfied. So this thing, independence between them are satisfied. This thing worked. Now we'll try to do the same thing, but in inverse direction. We will assume that Y is the cause and X is the effect. Again, we'll build a regression line, and then we'll analyze the distribution between the potential effect and the residuals. And we see very similar structure. And again, in this case, they seem to be independent. So both cases are independent. So we cannot make any conclusion. Both X can be the cause and Y can be the cause. However, not everything is lost. Let us now consider another case, the uniform distribution. Here, I assume the same type of the distribution for both X and Y. Let us do the same process. So we assume X to be the cause, Y to be the effect. We'll build the regression line. Then we analyze the distribution of the residuals. Again, here, no structure is observed. So this seems to be working. But now, if we do the same thing in an inverse direction, if we build the regression line, now it will look like this. And the distribution of the residuals will look like this. So here we now see a clear structure because the variation of the residuals changes when Y changes. So if we test now the independence, this will not hold. And in this case, we can assume that this is the correct answer. The similar picture will be observed if we use, for example, super Gaussian distribution. This is the distribution of the noise in one direction, seems to be independent, and in other directions. So here we can observe some dependent structure. Now, to finish, let us see the same results, but with the code example. So you should be able to see my screen now. Here, these are the independence tests that I will be using to calculate the independence between two variables. This is the same theory of the method. So we assume that this will be our structure with some function. We'll try two types of function. We'll try linear and cubic function. And we assume that the noise is independent of the causal variable. And we will be testing this independence. Here we can construct our data set. So I will generate 1000 points. I will take X that is normally distributed. Epsilon, my noise, is also normally distributed with some parameters. And then I say Y is a linear function of X and epsilon. Now I will be running this reset method. So I will construct linear regression. I will also construct the distribution of residuals and the potential cause. And then I can test the independence using this function. And in this case, we see they are independent. We'll try in another direction. Again, we can test independence, and again, it is independent. So this is the case when we have both variables distributed according to normal distribution, and we saw that we cannot identify the direction in this case. Let us now change the type of the distribution. Just run the code to make sure it works. Now what I will do, I will change the type of distribution for X, but I will keep the same, or let us make it the same as in the slides. So uniform and uniform. This is first direction. We test independence. They are independent. We assume the second direction. And now we see this shaped structure. And if we test independence, they are now dependent. So in this case, we can identify that there is a particular direction. In general, what we'll be doing, so for this method, we'll construct two tables. In the first table, we are testing this model, and we are testing the condition of the independence between X and epsilon. And we put a plus if they are independent. And if you try all possible combinations, here also in the code, I try the combinations with types of the distributions that are different. For example, uniform distribution for epsilon and normal distribution for X. And we see that in all of these cases, we observe independence. And this is indeed true because this is how we generated the model. X and epsilon were independent. Now, if we do the same in inverse direction, only this cell will show us the independence, and all the rest, there will be dependence between epsilon and y. Now, when we put these two tables together, and if we observe in the same cell plus, let's say here, plus in one table and minus in another, it means that the model is identifiable. So these are the results if I combine all of them together, and we see that there is only one unidentifiable case in this one, when we have both epsilon and the potential cause being normally distributed. Now let us see what happens if we work with another model, with the cubic model here. So I will take the normal distribution for both X and epsilon, and recall that this was the only case that was not identifiable for the linear model. Let us see what we'll get if we are working with cubic model. So this is what is changing. We are having the cubic model now. Regression in one direction, we are plotting the distribution of residuals. We test the independence, and as expected, they are independent. Regression in another direction, this is the distribution of the residuals. Now, to better, okay, I will first show this. If we now test the independence, they will not be independent. So this case that was not identifiable for linear model becomes identifiable for nonlinear model. And to better understand why do we have these types of shapes, here I show the regression in the transformed coordinates. So essentially, I will be using instead x and y, I will be using the coordinates x and cubic root from y. So here the relationship will be linear. This will be the data, and this will be the regression line that is constructed. So the reason why they are not independent is due to the way the points are distributed around the zero. And because at the point 0, we have drastic change in the shape. So here the lines can be easily approximated with linear. So the curve can be approximated with linear function with the same slope, but here it changes drastically. That is why this is the reason. So if you try to understand why it works like this, just try to build different graph and you will see why it gives this result. Now, if I summarize the same types of test for this nonlinear model, and I again consider this identifiability table, I will see that in this case, for cubic model, all the cases are identifiable. And in fact, the linear case is one of the most difficult. So this is the case where we can observe unidentifiability, but whenever the model becomes more complex, it is usually identifiable. The last thing that I would like to show is that this method, in fact, depends on the strength of the noise. So how big is the distribution, the variance of noise variable as compared to the variance of the causal variable. So in the original case, we had comparable variables, 0, 1, for uniform for both. Now I will change it. X will have the range from 0 to 15, and the noise will have the range from 0.5 to minus 0.5 to plus 0.5. So the relative variance changed. Let us now try the same process. In one direction, independence is true, and in another direction, again, independence is true. So here we can see that there is a slight inclination. However, this inclination is not enough for our statistical test to assume the independence between y and the approximation of residuals. So this method depends also on the variance, like the relative difference between variance for our causal variable and our noise variable. And that is all that I wanted to share in this series of lectures. So now I'm ready to answer the questions if there are any.
Thank you, Marharyta. So I'm opening the question part of the seminar. I have a few, but I will leave the floor to others first. Or maybe I can start with a first one. About this method to detect the proper oriented graph of dependency, you first assume that there is a first fully connected graph, and then you excluded some of the paths,
Yes.
and then you computed the direction, right? This
Yes.
was, yeah, exactly. So my question is about the complexity of such a method, because if we assume that we have, let's say, n nodes in the graph, then we have n squared edges, right? But if we consider all these triple of or all three nodes that could be connected in some directed way, then we can have something of the order n to power 3 of these triples per node, right? Because per each node you can have if you take just pairs of nodes, probably it is, or maybe it's n squared, right? Per node. So it's n squared per node. So in the end, you need to do something like of the order n to power 3 of tests, right? If you have a fully connected graph in the beginning, right, and if you have n nodes, right? So is it, according to you, is it something computational very intensive, or it is still traceable?
So you're absolutely right that this is computationally expensive, and essentially when the number of nodes grow, the computational time will grow probably exponential or something.
Oh, exponentially.
Maybe not. I mean, I'm not. Maybe not exponential. So I will not be giving the correct strict numbers here because I didn't check it. But you are absolutely correct that this the more nodes we have, the more complicated this process becomes.
Okay. Yeah.
So I didn't go deep. There are some alternatives to this algorithm, but I cannot say if any of them are faster or not, because essentially, more or less, we will be performing the same tests, independence tests. Maybe there are some alternatives that will be faster, but I cannot say now.
And maybe the second question, related again to the same example, is the question about the cycles. I mean, if we have some feedback causality bidirectional in the reality, then should it be identified as a 0th step or first step, just to exclude first the cycles, possible cycles, if possible at all, and then again, to create these directions and other, because if you have cycles, then if you condition on one variable, the other will be not changing, right? I think if you have cycles like a bidirectional causality, then perhaps it can somehow spoil the
The performance of this method.
The performance, or I don't know.
So
you know better probably what that spoils or not.
I didn't research this question yet, but so this algorithm was developed for learning structure of Bayesian networks or directed acyclic graphs. And all the theory we were talking about directed acyclic graphs. And as I said before, it is possible to consider these cases, but what I know, they are split into two cases like this. So most probably in the data set, there should be some time point or something like that when we'll be able to first identify the effect of X and Y, and then, because there should be some order in time, the effect of Y on X. Otherwise, we can, if it is happening at the same time, probably we cannot do it. So there are works in this direction, but I didn't study them yet. So I can only tell some guesses. This is one of the guess how it works. I cannot give more details.
Okay, and maybe the last question from me is the simplicity assumption, which you shown. I think it was slide, I don't remember, 15, maybe, no.
It's on the screen.
Okay, here, exactly. So it doesn't exclude the existence of the common confounder, right? Because
yes.
it can be, then there can be a common confounder that creates this kind of shape of the plot. But it doesn't mean that there is a direction between the X and Y, or Y and Z.
Yes, true. So this was for the case when we know that there is an edge and we need to orient it.
And there is no
confounder. Like this method is also based on no unobserved confounder. And then essentially I would say that this method is like the next step to the previous method. So we identified the skeleton, and now there are some edges left to be oriented, and we can now use this method. So like a follow-up, it doesn't make sense to start with this one, because if we have like 10 nodes and we start orienting the edges directly, so first we should identify the skeleton and then identify the direction, like skeleton, like for example here what I showed. Here we identified the skeleton, red edges show the skeleton, and then we can use that method to orient the edges that are not yet oriented.
Okay, clear for me. Thanks.
For now, while there are no questions, just maybe one more thing that I would like to say. We saw that we can identify the structure. For nonlinear functions, it is easier than for linear. And for linear function, there was only one case that was not identifiable. The final note that I want to say, so we did this identification with the RESIT method based on additive noise models. However, I think like 1 year back, there was, like just recently, there was a new method proposed that is able to solve this problem as well. So here, what I want to say, this is a very active research direction now, and the methods are being developed right now. Yeah, this is the final thing.
So even if there is a normal or Gaussian distribution of noise and dependence, I mean the confounding variable, then you can distinguish between
these two cases. Yes. Now there is a method that is able to identify this case as well.
Nice. Okay, so if so I don't know if there is no question right now. Just again, I would like to mention that the recording will be available online, and the reading is included in the presentation, which is on the website, I guess, right?
This is the link to my Google Doc.
The Google Doc, okay.
Yeah.
So perhaps we should put it in the additional material on the website directly. It is included in the presentation. I mean, this is the slide of the presentation, right?
Yes.
Okay. So thank you so much, Marharyta, for a very nice lecture and very clear presentation, and for availability to record it and store it for the future listeners.
Thank you very much for attention and for having me here for such a long time. It was a pleasure for me.
And